Okay, so the title of my talk is Surface Operators in the 6D2,0 theories. So these theories, these 6D2,0 theories, they're predicted by string theory. And okay, what they are? So they're usual quantum field theories, QFTs, with more symmetry, right? Extra symmetries. So in particular, we have conformal symmetry in 6D. That's some SO8 symmetry. We have supersymmetry. So this is 16 supercharges. And because these theories are conformal, they also have their special supersymmetries. So 16 special supersymmetries. And we have some R symmetry, which is SO5 in this case. So these symmetries together, they form an algebra, a super algebra. And this is what people usually refer to as the 2,0 algebra. So this is the name for these theories. And normally you might understand these symmetries as symmetries with Lagrangian, but in this talk, I'm not going to talk much about Lagrangians. You can think of them as putting constraints. Okay, so this means a number of supersymmetries. So there's 16 supersymmetries Q, right? So they sit in a representation of the SO6 Lorentz group, right? So in 6 dimension, your spinors are chiral, so they have dimension 4. So there's a 4 of the SO6 Lorentz, and they also transform under this R symmetry. So they transform in spinor representation of SO5. Okay, so in total, there's 16 of them. But okay, to get the counting right, you want to count the number of real supercharges. And you can only make real supercharges using two fundamental spinors. So in this case, there's twice that number. So this would be the 2,0 means 2 chiral, and now the name for the reality condition is symplectic Majorana fermions. Okay, so it just means the way you count these supercharges is twice the minimal amount in 60. So it adds up to 16.
Sorry, and could you also remind, I mean, it says, so SO5 has some isomorphism, right, to SP2 or something, yeah? So is
Yes.
it so this related to n equals 2, yeah? The 0, the SP2.
Yeah, it depends how you note it.
SP4, yes, yes.
Okay, but this is just the spinor representation of SO5. Or if you want the fundamental of SP4. Yes, so in 6D you distinguish between left spinor, so chiral spinors, and anti-chiral spinors. So this is 2 chiral supersymmetries and 0 anti-chiral supersymmetries. Okay. So what I was going to say is that you can think of these symmetries as just constraining the form of correlators. So for instance, if O is a primary, then as usual in a CFT, the 2-point function is constrained to take the form. So there will be some number which is the normalization, and then x1 minus x2, and this the exponent here is the conformal dimension. So this is a constraint from conformal group, but then you also have constraints from supersymmetries, which tell you that this operator must fit in some multiplet, and then there's also constraints from R symmetry. Well, just constrain the form of the tensor structure that way. Okay, so you can think of these symmetries as realized like this. And now, what I would like to tell you is, okay, what are these 2,0 theories? So the claim is that first there exists the free theory. So this is a theory without interaction. And then for the interacting theory, they're classified, they obey a classification by the ADE group. So A is like SUN, B is SO2N, and these are the exceptional group. And the claim is for each of these groups, there's a 2,0 theory associated with it. Now, a few properties. The first one is that for the interacting theories, there's no Lagrangian. Yes, so this means that you can show using a representation theory that these theories cannot have a coupling constant, or they can't have an exactly marginal deformation. So you cannot think of these theories as small deformation of a free theory, the way you would for n equal 4 to bearing small lambda. So yeah, exactly. So yes, so AN is equal to SU n minus 1, I think, or n plus 1. Well, okay, I mean, I'm not an expert, but this sort of AD classification arises in many contexts. One of them is these Lie groups, on the algebras, but also in singularities of there's other contexts in which these singularities appear. Yeah, I mean, I could tell you just the SUN, and that would be it, but maybe this suggests like a gauge theory, and there's no representation as a gauge theory, at least that I know of. And so the claim is just that there's a theory for each of these groups. Does that make sense? They're labeled by these. Yeah, it's a label. I mean, it's not that there's an explicit answer.
By the way, there's also, I think AD is also classification of like surface singularities. Yeah, I mean, Ricci flat surface singularities. Does it have, is it related to this? I mean, is it like kind of transverse space to this 6-dimensional theory is a complex surface or something? No?
Yes, I mean, if I remember correctly, the way it arises is Witten first was studying type 2B string theory on some singularity, singular manifold. And the way these theories appear is as singularities of complex surfaces. So there's a link there, but I don't know exactly what.
Thanks.
Well, I mean, I don't really know what to do with the Lagrangian if you can't use free field realization. If you can't talk about small perturbation. Yeah, but it's like you can talk about a theory which is strongly coupled, but then I don't know what the Lagrangian is for. Well, okay, maybe a better way to put it is there is no coupling constant. No Lagrangian has been written for it, and you know that it will be quite hard to write a Lagrangian because there's no limit in which this theory becomes free, and you can think of just genetic terms. Yeah, I mean, yeah. Yeah, you cannot. Yes. Can you repeat? No, I don't think so. When you don't know what would be the field, you don't know. Yeah. Yeah, there's no coupling constant, so strongly coupled. Okay. The next thing is, well, okay, so 6D is maximal dimension for a superconformal field theory. And this 2,0 algebra is a maximal supersymmetry for field theory. So if you have more supersymmetries, then your multiplets would involve gravitons or something like that. So it wouldn't be a field theory. So this is the maximal dimension. Then there's two explicit realization. That I'm going to talk about. So the free theory and holography. And the last one is that it contains surface voltages. So these theories contain surface operators. And this is what I'm going to emphasize. Okay, so this is a list of their properties. Why should we study these theories? So what I mean is that you can study these theories, so calculate observables using holography. So there's a description in terms of M theory on some background. Yeah, ADS7 process. So I'm going to talk about it in a moment. Why? So okay, so there's a few motivations. I think the most important one maybe is M theory. So M theory contains M2 branes and M5 branes. And the theory that describes the low energy dynamics of these M2 branes is a known 3D theory. It's called ABGM. Okay, so this is low energy. And the low energy description of M fibrins are these 2,0 theories. And it's the SUN theory. So if you want, this n corresponds to the number of M fibrins. Okay, so this gives you, okay, so the motivation in this sense is that by understanding better how to calculate observables in the 2,0 theory, we're finding a description for M fibrins, and we understand better the dynamics. And the other reason why this perspective is interesting is, okay, it makes contacts for surface operators. So we can have M2 branes ending on M5 branes. So if I draw a cartoon, it would look something like this. So this is M2. This is an M5 brane. And so this is a three-dimensional object. The boundary is two-dimensional and it's constrained to be on this surface of the M5 brane. So there it defines a surface. And it defines a surface operator. So if you want, by studying these surface operators, we're probing the interactions between M2 brane and M5 brane. Okay. There's other reasons to study the theory. Okay. The challenges our understanding of QFT. Well, the reason is, okay, usually when we study quantum field theory, the perturbative framework, we always use Lagrangian description. There's so weakly coupled theories. And here, this is an example of a theory that, okay, doesn't have this kind of expansion. And there's also, I mean, it's an open question what are the fields that describe it. There's a lot of indication that it's not a gauge theory. So understanding better these properties might help us to understand what other types of quantum field theories we can have. And the last point that I think is interesting is compactifications. So by compactifying this 2,0 theory, people have derived some dualities. For instance, famous one is the AGT correspondence between some 4D theory and a two-dimensional theory. So better understanding these theories might lead us to better understanding dualities in lower dimensional fields. I don't know. Yeah.
So the question is the relative proof?
I don't know.
That's
Okay, so this is my broad introduction to the 2,0 theory. What I want to tell you about is one way that we've tried to develop to study them, and it's to focus on surface operators. Well, the reason is that, okay, as I told you, they're supposed to capture interesting physics, but they also have a sort of good combination of simplicity, so you can actually calculate things, and being interesting. So what's important for us is that you can calculate them in many ways, through many techniques. So for instance, field theory, holography, you can use supersymmetry, things like deflective P techniques. I'm not going to talk about. They might be dual to scattering amplitude of strings, and maybe. So all these different perspectives on how to calculate them, how to think about them. If you combine them, you can hope to answer some questions like, what are the important observables? What are the interesting observables for this theory? And how do we calculate them? So, so this is the question that I want to answer, how to combine these things to find interesting observables, and how can we calculate them. And I'm going to focus mostly on field theory, holography, and supersymmetry. Okay, so the plan. First, I'm going to talk about the simplest observable, which is the sphere. And I'll give a description in field theory. So maybe that's more familiar to you. Then I'll do the same thing, but in holography. Then I'll use this to motivate a problem, which is how to find the holographic dual of a given observable. If I give you some, my favorite surface operator, how do I find its holographic description? So I'll make this precise. So finding all these M2 brain embeddings. And also a solution, which is how supersymmetry helps. And the last thing is I'm going to give an example of this, which is the torus. So hopefully there's a paper that should come out next week, roughly, about this. Okay. So the simplest example of the 2,0 theory is what I'm calling the free theory. So it's a theory with no interactions, and the way to define it is just to give the propagators. So free theory consists of the following fields. So there's d mu nu 2 form in 6D. There's psi, which is a fermion, and phi I, which are 5 scalars. So these scalars transform in the SO5 R symmetry that I wrote before. And also you can think of them. So this is the theory that describes the low energy dynamics of a single M5 brain. If I put an M5 brain in 11 dimensions, there's 5 transverse directions. So these are the 5 Goldstone bosons that correspond to the breaking of translation symmetry for this M5 brain. it's like a gauge field. Yeah. So it transforms under gauge symmetry. It has, you can have some field strength H. And I can write the propagators for them. So as I told you, this is fixed by superconformal symmetry. So it will look like constant delta ij. Notice here the exponent is also fixed by superconformal symmetry. So the unitarity fixes the dimension of these fields. And there's something similar for the other fields. Yes, so it's like the unitarity bound that fixes the conformal dimension. The same way that a free field has fixed conformal dimension. And for the 2-point function of B, you also have some constant which is related. You have some tensor structure which looks like this, and some indices antisymmetrized. And again, we have the same exponent. So you can read off that the dimension of phi is the dimension of B, and it's equal to 2. And okay, so my claim is that these 2-point functions define the theory. So I don't need to write down an action. And actually, there's some subtlety in writing down an action. But okay, if you're interested, just ask me later. So now using these propagators, I can calculate some surface operators. So first, let me write to you, define for you what the surface operators are in this series. So I have a 2 form. So this is really like a Wilson loop. So I have a 2 form, so I can integrate it over a surface. I just take the pullback. So B mu nu. Now I write the pullback. This is integrated over the surface. Now you see that B has dimension 2. I'm integrating over a surface, so the default thing is dimensionless. But because phi also has dimension 2, I can also write a more general operator where I also have phi I. I'll have some parameter n that I can introduce. And then I should integrate this against the volume form. So here H is just the induced metric, so determinant of the induced. Okay, so this is the most general surface operator in the free theory, and it's defined by the choice of embedding X. So it takes some sigma, some surface sigma into R6. We also have N, which is also a map from every point of the surface to R5. So it just chooses some scalar coupling. Yeah, so it can vary along the surface. So yeah. There's no ambiguity of ordering because this is an abelian theory. So there's no path ordering. These are just fields. They're not valued in some algebra. B is just a field. I mean, okay, I'm working in Euclidean signature and like, you should think of it as an action formulation. So I don't have like, I'm not thinking about this as an operator. Maybe there is.
So you are thinking about this as about something between
Yes. Yeah. Yeah, so in the same way that X defines an embedding of the surface in 6D, and defines an embedding of the surface in some auxiliary space, which is the space of scalar couplings, the choice of scalar coupling along my surface.
So you can think of this as a embedding of initial dimension.
Yes. I mean, it's not direct. So the transverse directions are not exactly n, but they're related. This is like the directions. Anyway. So I mean, this maybe it's like a parametrization. So you say, you know, if I'm talking about a sphere, this would be the Riemann sphere, and then I'm specifying the embedding in the R6 target space. Yes.
And this particular combination is because of supersymmetry, or what?
So this particular combination, I mean, you don't need supersymmetry for this. This is just the most general operator you can write. If you want to restrict that to a surface operator which preserves some supersymmetry, now this is an interesting question. And okay, let's say just for the plane. So I'm choosing this X to be just a plane in R6. Then the condition that this operator is supersymmetric would mean that n as norm 1. So this would mean that for the plane, this would be half BPS in that case. Okay, so this is the formulation, explicit realization of surface operators in the free theory. If you want to think about the non-abelian theories, they will still be described by some embedding X and N, but in addition, you have to specify other data, so you have to specify some representation of SUN. So let me tell you how to use this to calculate example of surface operators. So I'm going to take the sphere. So the sphere is, I'm just choosing the usual parametrization. Cos U, cos V. And then for the scalar coupling, I'm just choosing a constant. And all the other components vanish. Okay, so what do you do? Well, to calculate the expectation value, you will have, so I'm expanding this exponential. The zeroth order gives me 1. Then the first order will be 1-point functions, which in CFT just vanish. So the first order that contributes is when there is this thing squared. So it would look like propagator for B minus sign plus propagator for phi. And then there are higher orders. And because this is a free theory, all of these contributions exponentiate. So the result will be just exponential of this integral. And if you plug in this value, what you'll find is, okay, something like, if I'm careful about the factors, I think it's this. So this is the volume form, 2 copies of the volume form in the sphere. And then in the denominator, you have the distance, chordal distance. So Okay, something like this. Now this integral is really easy to do because, okay, this is just propagators between 2 points on the sphere. Because of spherical symmetry, I can fix 1 point to the North Pole. And what you'll get is, so.
You mean you are taking the integral of 1 over x minus x prime to the fourth, right?
Yes.
Okay.
And
yeah.
So this is the distance squared. No, you would get distance to the fourth, but 1 power cancels with the numerator. Yeah, just if you work out what this thing is explicitly. Okay, so I'm just using spherical symmetry to reduce this to one integral. So I'll have 4 pi for the area of the sphere, and then I also have symmetry along V, so times 2 pi. And I'm left with cosine u du over 1 minus sine u. And this is integrated between minus pi over 2 to pi over 2. And you see that when u is equal to pi over 2, this term diverges. So to do this integral, you just do change of variable. This is dx 1 minus x. This becomes minus 1 to 1. And this will give me a log divergence. Now, the way to treat these properly is to go back at the beginning, add some regularization, and then work out the result. But this will be equivalent to just adding something like epsilon over r here, maybe squared. Okay, if you do the integral, you get, so this is just 1/2, something like log epsilon epsilon over r squared. And now I can rewrite this. Oh, I should be careful. So here they can be also, so there's also a finite part. You can have some. So I can write this as some constant c, which depends on this epsilon times r. Okay, so the conclusion is that because of the presence of this log epsilon divergence, when you renormalize your operator, you acquire dependence on R. So the operator becomes, so the sphere operator has a conformal dimension quantum mechanically, and the exponent that is in the exponent of R is the same thing as the log epsilon divergence, and it's known as the conformal anomaly. Right, so this is a generic feature of surface operators, and it's really analogous to the 2-point function of local operators that can also have some anomalous dimension. What it means in practice is that this constant c, because it depends on epsilon, is not well defined. So there's no, in general, there's no finite expectation value to calculate. There's just the anomaly. And in fact, the anomaly is known more generally. So now this is not just for the free theory. This is true in general, that the anomaly is up to some factor. It looks like some constant times the Ricci scalar plus A2. And now these are curvature invariant associated with the surface. Something like this. This is integrated over H. This is integrated over the surface. So if I specify to you what is the embedding of the surface, what is n, you can calculate this integral and you'll get some linear function of A1 and A2. And these constant here, this is the extrinsic curvature. R is the Ricci scalar of the surface, so it just calculates the genus of the sphere of the yes.
What is A?
Yeah, so these are just constant.
No, A.
Oh, this is sorry, this is the anomaly. So it's the exponent here. And so for this example, A is equal to 1, or maybe minus 1. Yeah. So it's a coefficient of the log epsilon divergence. And these coefficients here are independent of the geometry. And so they only depend on, say, n, the rank of the gauge group of SUN. And they're known for any n, exactly. So the upshot of this is that given any embedding, you can go ahead and calculate the anomaly directly in any theory. And so you can identify, for instance, which operators have vanishing anomaly, which is what I'm going to come back to. Okay, I just have.
Sorry, but when you say any theory, you mean you just add more of these gauge fields, kind of B fields, yeah? Or what do you mean by any theory? I mean, I'm saying this kind of supersymmetry, it only has just one multiplet, yes, or not? One type.
There's many multiplets, but if I'm not looking at the free theory, if I'm looking at some other ADE theory, I don't know a field realization, but still, you know what these coefficients are. These are derived in some other way.
Yeah, I meant one multiplet. I meant this B fermion scalar, right? There's no like matter multiplets or anything, right?
Yes, but so there's a tensor multiplet. There are other multiplets like the stress tensor multiplet, but I mean I don't know how they're related to these coefficients because yeah, I don't know. What I'm saying is that the formula, the explicit expression I wrote for V, then doesn't apply, but still this formula is true. The anomaly is. Okay. Right. So now let me talk about holography for a bit. So how these surface operators are represented in holography. So we use ADS-CFT. This is the claim that 2,0 theories at large M are described by M theory on ADS7 cross S4 background. So I'll write down exactly what this says. And there's a similar claim for surface operators. So surface operators, their holographic dual is given by M2 branes. Such that on the boundary of ADS, you recover the surface operator. So let's say with boundary conditions. So ADS7 cross S4, I can take the following metric. So what is this? Y is just the norm of this vector yi. Yi are five components. So if you want, this thing is like the metric on R5. Then you divide by the norm squared. So it's like the metric on S4. And the radial direction of the space becomes the ADS coordinate here. So okay, at y goes to infinity, you go to this is the boundary of ADS. So okay, at y equals to infinity, so boundary, and this term will drop. It's finite. This term is proportional to y, and it's conformal to the metric on flat space. So at the boundary, this is R6, and yeah, okay. If you want maybe a
This mu runs from here. Yeah, does mu run from 1 to 7 or
oh, sorry.
1 to 6?
Mu is from 1 to 6. So this is just flat space. And now if I expand this, okay,
Okay.
I goes from 1 to 5. And if you expand this, this will be
So
dy squared plus y squared then some metric on S4.
okay.
So you can take this dy squared
Yeah,
and put it there, and it becomes a metric on it. Yes. Well, okay, that's fine. Okay, so the boundary is at y goes to infinity, and okay, so let me just give you an example of what the sphere is in this case. So for the sphere, so we start with the action for an M2 brane. This action is proportional to the volume form of the M2 brane. So there's determinant of G, which is the induced metric on the M2 brane. There is a term here which couples to like a tree form C, which is the tree form of 11D supergravity, but this term doesn't contribute in this case, so I'm just ignoring it. And the coefficient of proportionality is just the tension of the brane. Okay, so to calculate this action, I need the induced metric. So that will depend on the embedding of this M2 brane into the ADS geometry. And roughly, okay, if you think of ADS as a disk, you have the boundary, this is like y equals infinity. You have a surface operator with boundary conditions at y equals infinity. So I'm setting a position on the boundary, which corresponds to my chosen surface. And then what the brane does is minimize its volume. So it will look like something like this. It's extended into the ADS direction. This is the radial direction is like y. And then at some minimal value for y, it will close up and become a smooth geometry. And so this is what we want to solve for. We want to solve for the embedding of the M2 brane.
Sorry, and the original S2 sphere, that's at the boundary, yeah? Sits or where?
Yes, so the boundary is in S2, and the extension into ADS will be some three-dimensional
Yeah, okay.
brane. It's an M2 brane. Okay, so for this case, okay, what I should do is simply write down an ansatz for the embedding, calculate the induced metric, so I can write down the action and then solve for the equations of motion. So the ansatz in this case, what I'll do is just take my ansatz for the sphere and assume that the radius of the sphere can depend on this ADS coordinate. Cosine u, cosine v. And then the other coordinates are the same thing, but just with the other parameterization. And then you can calculate the action, which will look like integral dy, and then I think you have f squared okay, this might be wrong, but I think it's this. And then, okay, this is an integral over the whole N2 brane, but you have F2 symmetry, sphere symmetry, so that thing will just give you a factor of 4 pi. Oh, sorry, that's R. Okay, and okay, I think anyway, there are some factors. Now, what you should do is calculate the equations of motion for R and solve for them. But in general, because this action is nonlinear, the equations of motions are very hard to solve. So in this case, we know the solution. So the solution is just R is equal to square root of R squared, the radius on the boundary, minus 1 over y. It's a simple solution. But the equation of motion, if you write it out, is quite complicated. So the point that I want to make is that there's very little known M2 brane solution. The only examples that I know of are the sphere, this one, and there's a second one, also for parallel planes. Well, the reason is that, I don't know, these equations normally are like nonlinear PDEs. If you don't have symmetry, they're really hard to solve.
Yeah, PDEs.
I mean, if you take an arbitrary surface, it doesn't preserve translations, right? So you won't have killing vectors. I mean, ADS have these symmetries, but they're not preserved by the surface, your choice of by the N2 brane.
Yeah, but in the case of geodesics, we have vectors to project on the geodesics junction of the vector. This is a vector of such construction.
I mean, to be honest, I don't exactly know what you mean. Maybe if you explain to me later, because I'm not aware that there's a simplification. There's a simplification with supersymmetry.
I just wondered how the solution was found.
In this case, you can find it by a conformal map, because this is a conformal theory. The sphere is like conformal to a plane. And for the plane, the solution is trivial. So you just do a conformal transformation and you get the one for the sphere. And the only other solution that I know of are these parallel planes. So, okay, I don't know if there's a cheat code, but I don't think there is. I think this is just a hard problem. And okay, I'm almost out of time, but I wanted to say we found a way to use supersymmetry to make this problem much easier. So I'll just tell you roughly what you can do. And then, yeah, if you're interested, I can tell you about the example later.
Sorry, and in that effective brain action, there's no like contribution from the form of supergravity?
Well, in all the examples that we looked at, there's no contribution from the tree form. I think it's general because you well, okay, the reason the tree form doesn't contribute for the sphere is that it's extended in only one direction on the full sphere. So it cannot like measure any non-trivial C because it's a tree form. So you will need an M2 brane that's extended in at least 3 directions on the sphere. And Yeah, I'm not sure about the general statement. I'm not sure that it can never contribute, but certainly in all the examples that we've looked at, there's no contribution.
But the general answer is you just take the integral of the three form over your brain. Yes, that's the general. That's what
yes. So you know what the this three form C that I wrote. You can write an explicit expression for it, right? Because the flux is known, so you just pick a three form, and then you should calculate it, pull back to the surface, and that would be your action. But I think it, at least in all the cases that we've seen, it vanishes.
Yeah,
So I don't know if it's a general statement that it doesn't contribute for M2 brains in this geometry. Okay, so very briefly, so the way we simplify this is that we've shown that for a class of BPS surfaces, so surfaces that preserve some amount of supersymmetry, there you can write down BPS equations. BPS surfaces. There's some first order differential equation that they have to obey. And the equation looks something like this. So G again is the induced metric. Then there'll be some Levi-Civita tensor on the M2 brane, the metric. Now there's this three form phi, which I'll tell you in a second. Okay, so they have to obey these equations. And here, okay, x is any of x1 to x4 and y1 to y3. So x takes value in some 7-dimensional space. So it's a subspace of this full ADS7 cross S4, meaning the BPS surfaces are restricted to subspace. And the subspace is ADS5 cross S2. This is imposed by supersymmetry. And the tree form here that appears is something like constructed from the two symbols. It looks like something like this. And this has a natural interpretation. If you know about it, this defines a G2 structure on this space. So it's some object that's associated with this ADS5 cross S2. And now you can think of these equations as being a sort of generalization of the condition for homomorphicity. So if I just drop one index, you can think of this could be the complex structure of the space. So this would be the analog of like the holomorphicity conditions for holomorphic surface. So it's a generalization, but to G2 manifold. And the point is that for at least some examples, these equations are very easy to solve. And so we solve them for one example, which is a torus. And so we found a new family of solutions which are associated to this torus. And what's interesting about it is that the torus has no anomaly. And that means that it can have non-trivial expectation values, unlike the case for the sphere, which I told you about earlier, where the constant that arises in front has an ambiguity because of the anomaly. In this case, there's no anomaly, so there's no ambiguity, and you can calculate the expectation value. And well, okay, maybe that's it. Okay, so non-trivial expectation value. it's interesting for many reasons, and in particular, it's related to a sort of potential for strings in 16. So briefly, my conclusion. Okay, I would have liked to talk more about the torus, but that's okay. Okay, we can define interesting observables. The reason is that this depends only on, as I said, looking at the anomaly, which is known for any theory, and it only depends on the choice of embedding. So for the torus, I know that there's no anomaly for any theory, so I know that there's a finite expectation value to calculate. What's surprising to us is that the expectation value was non-zero. And we can also calculate it at large n using holography. So this is explicit computations. So there's a few questions that you might want to ask. The first one is that, okay, this is leading order at large n, but the natural thing to do is, can we calculate subleading in n? So in the case of string theory, these holographic duals are also known for many examples of Wilson loops. And in some cases, we can also calculate subleading corrections in n. So it could be interesting to know if we can do the same thing for M2 branes. Actually, it's been done in a paper from Arkady and other collaborators last year for the sphere. But for other operators like the torus, we don't know. And let's say, so an interesting problem for me is to look also at other geometries which can be interesting. So there's the case of the torus, which doesn't have anomaly, but there might be other geometries. And in particular, we found another geometry, which is a sort of a crease. And it also captures something like string potential. And it's an interesting observable, but okay, maybe I'll talk about it another time. And the last question would be that much of the analysis that we've done, so the analysis of anomaly and constructing BPS observables, this is also can also apply to other theories. So in the paper where we show this, we also show that these BPS surfaces can be constructed in 4D n equal 2 theories or 4D n equal 4 theories. So you can ask, okay, do these surfaces also have an anomaly there? And can they have some expectation value? And of course, for 4D super-Young mills, n equal 4 super-Young mills, we have more tools to study them. It would be an interesting question to understand them there as well. Okay, let me stop.
Thank you. Any questions?
Sorry, so BPS surface here, you mean like three-dimensional surface, yeah? So this thing that extends inside ADS, yeah? This is what we're talking about.
You mean in other trees?
No. I mean for BPS surfaces, what you on the left part of the blackboard.
Yes.
Three-dimensional guys.
Oh, okay, sorry. I was a bit so imprecise. This is the holographic dual of these BPS surfaces in the M2 branes over these equations. It's not these BPS surfaces, it's the holographic dual.
Okay. So holographic dual, you mean like extension inside ADS or what?
Yes. So okay, you have some. Yes. Okay. So these are really the coordinates of radius 5 versus 2, and you impose some boundary condition at the boundary of radius 5, that these coordinates approach the surface that you define on the boundary, and this is the extension of the radius. So
Yes,
this,
you were talking about the sphere shrinking inside ADS. Does it obey this equation?
for the sphere, well, of course, the plane obeys these equations. The sphere doesn't. Yeah, it's a different class of surfaces.
But your torus does, or
The torus does, yes.
okay.
I mean, okay, this is a big class of surfaces, but it's not all the detailed surfaces. There's other surfaces, but there's also generalization, previous generalization of the sphere that is less supersymmetry. They're like surfaces located on some tree scale. So they obey a different equation.
Yeah, I think these ones you wrote, these are like calibrated with respect to the 3 form or something like that. Yeah.
Yes, yes, exactly. But this is stronger than just the calibration equations. So the calibration equation would just tell you that the pullback of phi on the M2 plane is given by the volume form. But because this phi is a G2 structure, you can actually show that you have, this is like 7 times 3, so 21 equations. You can show that the surface needs to obey all equations.
Okay, I think I missed what you want to match in your holography dictionary from one side to the other one, from your gauge theory to the theory of branes in the M theory. So what are the observables that you would like to match?
Yeah, okay, so sorry. The problem that I wanted to talk about is given a surface in field theory, so a choice of embedding, how do you find the corresponding M2 plane embedded in holography? This is a hard problem. The dictionary also tells you how to map the expectation value of the surface operator to the action of the M2 plane. So I didn't tell you, I didn't calculate the action for you. So what would be the expectation value of the surface operator? But once you have the embedding.
So it's not like in the standard DS5 cross S5 holography when you have you wanted to match the conformal dimension in the CFT of the operators to the excitation of the strings on the other side. Here is you want to match it with the action.
Well, I think this. I mean, I'm not looking at excitations of the string. I'm not trying to look at small excitation of the string. I'm giving you the string. The equivalent would be, say, taking the circular Wilson loop or some Wilson loop located on some manifold. So it's a non-trivial curve, and then I'm asking what's the minimal surface that ends on this curve. So it's a different question than trying to calculate the spectrum of excitation around the cluster.
And if you reduce your M theory on a circle and you get to string theory, can you formulate such an analog problem with excitations? Or
I don't know.
Okay, thanks.
Are there any questions?
So it would be interesting to try to compute 1 over n corrections to that surface, right? So at least to see what you can get in this case.
And I think what's interesting is, okay, because we know the anomaly exactly, we expect to get the finite answer also for one of our interactions. And I think the question is whether we can actually get them in a closed form, do the problem completely.
Okay.
But there is also,
Yeah. Go ahead.
yes.
Okay, good. Let's then thank the speaker again.